All right, welcome everybody to our first asynchronous class for PHYS 413, Quantum Mechanics. Thank you all for joining me here. Obviously, this switch to online was a little bit surprising for all of us, as is the sound of jet fighters flying over my house. I don't know if you can hear those. Just a few notes before we get started. This is being recorded, so one of the reasons I'm doing this on YouTube is so that it will automatically create a recording of the stream for students to access later. You can interact with me through the chat feature, so just below this video, if you're watching it on a computer device, on a mobile device, there should be below the video a chat section, so you can say hi in the chat to let me know that you're here. I will let you know that I was testing this yesterday and the stream is delayed about a minute, so whenever I say something, you are hearing it about a minute later. So I'm going to keep that in mind as I look over at the chat window, that y'all are responding to things that I said a minute ago. In the chat, I've posted a link to this Jamboard. This is our whiteboard, so you can access this after class if you want to as a record. Basically, throughout the rest of the semester, I'm just going to be adding to this. I can add more frames to it as I need to. And so that'll be another record of what we're doing here in our virtual classes. Let's see. I think that's about all of the business I needed to talk about. So let's move on to some quantum mechanics. Okay, I just saw Emily's hi appear in the chat, so I'm glad y'all can hear me. Let's see. So what we're going to talk about this week is really one of the most important problems in quantum mechanics, and that is the harmonic oscillator. So this is the harmonic oscillator. It will work on my screen handwriting. There we go. You know this from classical mechanics as the spring problem, right? You know in physics we love our springs. So the idea is that you've got a spring with a mass attached to it. We describe the mass at the end based on how much mass it has, and then we describe the spring based on the strength, the stiffness of the spring, right? The spring constant K. And so you've got a force from the spring that is negative, the spring constant times however far the mass moves from equilibrium. So this x here, x equal to 0, is wherever the equilibrium point is. And so in classical mechanics, it's easier to work with this in terms of the force because you can set this up as Newton's second law, right? You can set this equal to the second to the mass times the second derivative of the position. And we've solved this. You've probably solved this a dozen times by now. You need a function, x here. You need this function to be arranged such that when you take two derivatives of it, you get back the same function multiplied by a negative. And that, of course, is sine and cosine. You know by now that sine and cosine are basically the same thing. So we can just write this as an amplitude times cosine of an angular frequency times the time. And if you plug this into this differential equation, you end up getting that omega is the square root of the spring stiffness divided by the mass. And so in quantum mechanics, we actually prefer to use this omega over the K. So we're going to say goodbye to the spring stiffness K in just a few minutes and work only with this omega, because it makes the quantum math a little bit easier. And anything we can do to help ourselves with the quantum math is a lot better. So for quantum mechanics, instead of working with the spring stiffness and with the force, we're going to work with the potential energy instead. So in this case, our potential energy, it's easiest to write it as 1/2. That's there for the calculus. When you take the derivative of this, you need to get the force, times the mass, times omega squared, times x squared. And it looks a little funny at first because it's a little more complicated than that force equation was. But that's because this omega is going to end up being nicer for us. And if you think about it in terms of the kinetic energy, right, kinetic energy is 1/2 mv squared. You can kind of think of this x squared omega squared as almost kind of like a velocity, or maybe it's the velocity that's kind of hidden inside the potential energy, something like that. Excuse me. When you plug this into the Schrodinger equation, right, you're trying to get out the energy eigenstate. So you're trying to get out negative h bar squared over 2m. Right, this piece is the same for everything. We're trying to take psi, the wave function. Actually, our textbook calls that phi, doesn't it, for the energy eigenstate? So we'll call that phi. We're trying to take second derivative of phi plus the potential energy times phi, going to equal an energy level times phi. So this is where phi is the energy eigenstate. It's not just any old wave function. It is the special wave functions that remain stationary throughout time. Well, the wave functions don't remain stationary. The wave function modulus squared remains stationary. But the important thing is these are the special states that have that energy level attached to them, right? So these get an index n attached to them. So this n is going to run anywhere from 0 to 1 to 2, all the way up. It's going to be any non-negative integers. So I think math calls those the natural numbers. Math majors, let me know if that's the appropriate name for those, the integers minus the negatives. And it turns out this is a differential equation we can solve. When you plug in this v with an x squared into this v over here, it turns out we can solve this. The solution method is not the most straightforward thing in the world, so I am not going to reproduce it here. It's available on your it's available in your class textbook. There's probably a million different versions online in video and text format. But when you go through the process of solving this thing, you end up with some pretty interesting properties, which is why we're interested in this problem to begin with. The first interesting property that you end up with, there we go. The first interesting property you end up with is the energy levels themselves. So these energy levels, right, this En, oh, I missed an N on the E there. There we go. These energy levels themselves end up being pretty simple. It's even simpler than the, okay, Alyssa is confirming that natural numbers are positives, whole numbers only. Okay, got it. So, so these energy levels, they end up being simple, even simpler than the infinite square well. You remember how straightforward the infinite square well was? Well, this one's even better. What you do is you take this omega, right? This is sort of your fundamental scale for the problem, is the fundamental frequency of the potential energy. You multiply that by h bar. This is a special combination because h bar times omega is always going to give you an energy. And so we call this the energy quantum. Quantum. There we go. We call this the energy quantum for the problem. And what you do is you take this energy quantum here and you just multiply it by a number. The number you multiply it by is just the energy level plus 1/2. I didn't leave myself enough room there. So this energy level is going to be the number, the level, plus 1/2. So for n equals 0, it's going to be 1/2 of h bar omega. For n equals 1, it's going to be 3/2 h bar omega. For n equals 2, it's going to be 5/2 h bar omega. So in other words, each time you go up in energy level, from 0 to 1 to 2, etc., you're adding an amount h bar omega. So you can think of this, let's use yellow for our energy levels. How about that? You can think of this as sort of like you start out with an energy level here of 1/2 an h bar omega, and then you go up an energy level and you're going to add h bar omega. You add another energy level, you're going to add another h bar omega. You add another energy level, you're going to add another h bar omega. It goes up by the same amount each time. That's drastically different than any other problem we've seen in this class. So the infinite square well, you might remember, it goes up like n to the second power. It goes like up like n squared. So first you have a jump, then you have a bigger jump, then you have an even bigger jump, then you have an even bigger jump. When we get to the hydrogen atom in the next couple of weeks, the jumps are actually going to get smaller. You're going to have a big jump, and then a smaller 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 jump. because the electron is approaching, escaping the hydrogen atom. But the harmonic oscillator is unique because these energy levels are evenly spaced. There's, to my knowledge, I could be wrong about this. I'm happy to be proven wrong about this, but to my knowledge, there is no other problem in quantum mechanics that gives you evenly spaced energy levels. That's pretty cool. That means if you set up this potential energy in a laser cooling system or in some kind of experiment or something, that means that you can get these nice evenly spaced energy levels. It's nice and easy to control. It's easy to predict. It's easy to work with. So what we'll take a look at next is the wave functions, these stationary states phi n. Let me give just a minute for the stream to catch up, and y'all let me know in the chat if you have any questions so far. All right, let's go take a look. I'll wait for those chat questions to come in. Let's take a look at the energy eigenstates phi n here. Remember, these are the special wave functions that you can construct where the real and imaginary parts of phi will oscillate back and forth, but the overall psi squared, the overall modulus squared, is going to stay the same. Let me pull up my notes on what I need for that. Okay, yeah, that's right. All right, so let's take a look at what the energy eigenstates look like. So the energy eigenstates, these phi n's, they've got three pieces to them. They've got, actually, let me pull up the actual equation so I know what I'm looking at here. Oh, there we go. Okay, cool. Nope. Okay. So there's three pieces to this. The first piece is a normalization constant, right? You remember that each of our wave functions needs to have a total area under the curve of 1. So if you take integral of any of these things modulus squared from minus infinity to plus infinity, the total has to equal 1. So there's a normalization constant. Then we multiply by something called the Hermite polynomials. Hermite polynomial is a special kind of function. We'll take a look at what they look like in a second. But those each have an index n, and that's going to be a function of x. Then we're going to multiply that by an exponential of e to the negative x squared over 2. Okay? And what that ends up doing is this is the thing that guarantees that the total area underneath your wave function is equal to 1. This is the thing that gives the wave function its wiggliness, right? Because a polynomial is going to have maxes and mins. And then this is the thing that ensures that your wave function is going to die down as you get to plus infinity or minus infinity. And I am double checking on what this normalization constant is because yeah, that is not the most straightforward thing ever. Oh, okay, there it is. All right, I found it. Good. So let's take a look at each of these pieces. So the normalization constant is going to depend on n, but it's just a constant, right? It's going to be the same thing every time you work with one of these functions. So this thing is a pretty wild combination. You take m omega, so the thing's mass times the angular frequency omega. You're going to divide by pi h bar, and then we're going to take this whole thing to the 1/4 power. That is a pretty unique number. I don't think you ever get quite this combination in any other problem, but this is basically what the math spits out that the normalization needs to be. But we're not done yet. We're going to take 1 over square root of 2 to the power n and then n factorial. So we're going to have 1 over square root to the n factorial. So this is the thing that keeps it from growing out of control as you get n higher. Let's see. So we'll have the normalization constant equal to this thing. And then the next piece is the Hermite polynomials. Very good. Sorry, I've got stuff popping up. I forgot to open up my Jupyter notebook earlier. The Hermite polynomials are an interesting bunch. They are a set of polynomials. They're actually going to be a function of a dimensionless version of x. Oh, goodness. Go away, Windows. There we go. They're actually going to be a function of a dimensionless x. We're going to call this thing psi. You can laugh at me if you want. This is how I write a psi. It's also how I write a quarter rest. Okay. So we've got a commenter in chat saying we can construct all a family of isospectral Hamiltonians in the context of position-dependent mass systems that possesses the quantum harmonic oscillator spectrum. Okay, that is good to know. Let's see. The math. I should say the math that you get out of the harmonic oscillator problem is incredibly useful across a whole bunch of other problems, right? It's not just useful for this problem, it's useful for a whole bunch of other stuff. So anyway, the next piece is the Hermite polynomials. These things have an index n that matches with the index n over here. That just indicates how complicated these things are going to get. So n is going to indicate the order of the Hermite polynomial. So if you've got the 0th Hermite polynomial, then you've got just a constant. You've got x to the 0 power. If you've got the first n equals 1 Hermite polynomial, then you've got x to the first power. If you've got n equals 2, then you've got x to the second power, x to the third power, x to the fourth power, etc. The Hermite polynomials just differ in terms of what the stuff is in the polynomial itself. The way you get these is actually pretty neat, because basically what you do is you get the first two. So your 0th one is going to just be, copy error, there we go. The first one's just going to be 1. So the first Hermite polynomial is just a constant. That's the 0th one. The first one, n equals 1, is going to be 2 times your input variable, your psi here, right? And then the way you get the next one is just through a recursion relation. What we mean by a recursion relation is that this is going to depend on the previous Hermite polynomial, so HP of n minus 1, and it's going to depend on the previous one before that, HP of n minus 2. Meaning all you need are the first two, right? So if you have 0 and 1, you can use these two to construct number 2. You can use 1 and 2 to construct 3. You can use 2 and 3 to construct 4, etc., etc. It's actually very similar to how you construct the Fibonacci series, right? Because you're adding the previous two numbers in the Fibonacci series. The only difference is we have to multiply these by a couple of things. We're going to multiply this one by x. Excuse me, I have to call this psi for dimensionality's sake. So this one's going to be psi. Sorry, I'm double checking my factors here. Oh, goodness. We went over these recently in my numerical methods class, so I am relying on that useful bit of information. Come on, Brian. Here we are. There we go. Excuse me, that's a 2 times psi. There we go. I know I was forgetting something. That one's going to be 2 times psi, and then this one is going to be a minus 2n minus 1 times the one from 2 times ago. So we've got a 2 psi times the previous Hermite polynomial minus 2 times the index minus 1 times the Hermite polynomial from 2 times ago. So it's kind of like the Fibonacci sequence if you squint a little bit, because you're taking the previous 2 numbers and combining them to get the third one. And there is some relationship between these and the Fibonacci numbers. I've never actually seen that explained, but I see it referenced in a lot of textbooks. The only other piece we have to think about is this psi here. The way this psi works is that the Hermite polynomials are invented by mathematicians, which means the independent variable here needs to have no units. And so we have to transform our x into a dimensionless number. I have to take x that is units of meters and transform it into a thing that doesn't have any units. And the way you do that is just by combining all your other constants in such a way that you get an inverse length, and that ends up being a square root m omega over h bar. And basically, if you work out the units on these things, you end up with inverse meters. So this is a thing, square root m omega over h bar has units of inverse meters. It's going to cancel with the meters in the x, and your psi is dimensionless. And then over here, the last piece you have is this exponential piece. Now that we've defined psi, I can officially replace this x with a psi, because that has to be dimensionless as well, right? Because you can't take an exponential of something that's got units of meters. It's got to have units of, it's got to have no units. It's got to be dimensionless. So anyway, all that to say, this is an interesting construction, right? This is a really interesting thing to piece together, because you have the normalization factor, you have the Hermite polynomials, and you have this exponential thing that causes it to die down. But rather than just write this down and hope you can imagine it, why don't we take an actual look at it? I'm going to open my Jupyter notebook. This will take me just a second. So feel free to take some time to post questions and comments in the chat while we wait for Jupyter to come up here. Because once you can actually visualize these things, it's notably easier to work with. I mean, so is everything in physics. That's why we have coding in our physics classes. All right, here we go to our beloved Jupyter notebook. Now, there's a few of you who are in quantum mechanics and who are in PHYS 251RI research methods. And so this project I'm bringing up here will look rather familiar to you. There's PHYS 12. Yeah, there we go. PHYS 251RI. And we'll go down to quantum harmonic oscillator. So if you're in Physics 251RI, you'll recognize this this setup here. Let's see. For the sake of visibility, why don't we Control plus make this a little bit easier for folks to see in case they're on mobile devices. So here what we're going to do, so remember there's these 3 pieces to the wave function, right? So we're going to define the wave function psi. It's going to take in 2 arguments. It's going to take in the energy level n. Ooh, CatDog is letting us know that we live in a simulation. Okay, that's, yeah. Going to report that. There we go. There we go. Alrighty. Spammers taken care of. Let's see here. So we are going to so we're looking here at this psi function. So we're taking in an index n. So this is our energy level, and this is our position. So remember, n is, we're putting it in here, we're passing it here as a variable, but it's a constant, quote unquote. You can't see my finger quotes, but it's a constant in the sense that it's the same throughout the entire wave function. N is not suddenly going to change in the middle of the wave function. Then we've got our position x here. That's pretty straightforward. So first we start out with the normalization constant. Here's all the pieces that I referenced earlier. There's the 2 to the n factorial. We've got our 4th root of pi in here. We're making life easier for ourselves here by having the mass and h bar equal to 1. And so our psi is just going to be the normalization factor times the Hermite polynomial times the exponential factor. And so all that remains is to get the Hermite polynomial. So we're using that recursion relation to get a clever way to get the Hermite polynomials. Remember, you only need the first two. So we've got the n equals 0 Hermite polynomial equal to 1. We've got the first Hermite polynomial equal to 2 times the input variable. And otherwise, it's going to be based on the recursion relation, right? So we got 2 times x times h n minus 1 minus 2 times n minus 1 times h of n minus 2. And so basically this function just keeps calling itself back and deeper until it gets down to n equals 0 and n equals 1. Now, one of the things that's interesting about this, if you take a look at the way these are set up, this is an even function, h0. This is an odd function, h1. So whenever you take these, you've got an even function and an odd function times x, which makes it even, or you've got an odd function and an even function times x, which makes it odd. So this is always going to be even or odd, right? We're never going to mix together powers of a different parity. So in a Hermite polynomial, all of the powers are either even or odd, x squared, x fourth, x sixth, x to the 8th, etc., or x to the 1st, x to the 3rd, x to the 5th, x to the 7th, etc. That's one of the neat things about the Hermite polynomials, is that they're always even or odd. That's a design feature. Okay, so let's take a look at how we're going to generate this image down here. So we're going to take a look at the first 4 psi n's. We're going to take a look at psi 0, psi 1, psi 2, psi 3. We've got psi 0, psi 1, psi 2, psi 3. And so basically we're going to loop over a whole bunch of values of x, and then we're going to append to those these values that we get from calculating psi, and then we're going to plot them. Now, I've already gone ahead and run this and saved it, so we don't have to wait for this thing to run. And so here we've got our graph of the wave function. So these are the phi n's that we get out for n equals 0 through n equals 3. Let's start with n equals 0. You notice this one is just the Gaussian. It's just the e to the negative x squared over 2, because that 0th Hermite polynomial is 1, right? So there's really no wiggliness going on. It's just this exponential envelope here. For n equals 1, we get a little bit more interesting. We get a peak and a trough, so we get 2 extrema. For n equals 2, we get 1, 2, 3 extrema. For n equals 3, we get 1, 2, 3, 4 extrema. So the way to understand this is anytime you've got these psi's of a certain n, that n tells you the number of bumps that you have. You could also think of it as it tells you how many zeros you have. So n equals 0, it never crosses the x-axis. These tails die down exponentially, and so there are no zeros there. For n equals 1, you've got 1 0 right here in the center. For n equals 2, you've got 1, 2 zeros. For n equals 3, the red one, you've got 1, 2, 3 zeros. And so it's really neat because this tells you basically everything you need to know about the wave function on a conceptual level, right? Because you just need to know, how many bumps it has or how many zeros it has, which is pretty cool. And you can take this to an extreme, right? So for example, I could take the 20th energy eigenstate, right? So let's suppose I set n equal to 20 here, and I want to graph that. This one will take you a little while to graph, which is why I've gone ahead and done it. And you notice you get 20 zeros, right? So you're getting a lot of bumps here. The interesting thing, though, is because of the way the Hermite polynomials interact with the exponential envelope, you always get your highest peaks over here at the end, and you get your lowest peaks here in the middle, right? We can kind of see that over here, maybe a little bit, that these two are a little bit more extreme than these two, but this really showcases that there's an envelope that goes around this thing that makes this kind of U pattern. And that's significant because that's what you would expect to see in a classical system. You would expect the particle to hang out a little bit longer at the edges as it turns around than you would in the middle where it's zipping by quickly. And this is really a neat result because it shows us that the particles, as you get higher in energy level, are going to start behaving more like classical particles. So that's a neat visualization there. I will make this file available to you in our class folder. But that's the neat thing about the harmonic oscillator energy eigenstates, is that they have these really neat features. Okay, let me tell you about a couple other things that are important about the harmonic oscillator. Again, I'm not showing you where these wave functions come from. I'm just showing you what the results are. Your textbook gives you an excellent description of how they get derived, of where we get them from. When you derive these, our textbook and most every derivation uses these by defining what are called ladder operators. So we're just going to take the rest of our time to look at these things called ladder operators. Oops, there we go. The way you define these is we call these A and A dagger. The dagger here just indicates that this is the Hermitian conjugate of this one. Remember, that was a big vocabulary word we had at the beginning of the semester, where if you represent these as a matrix, you're taking the transpose of the matrix and the complex conjugate of everything. The way you define these, and this is not something I expect you to know, this is something that you look up, just like I'm looking it up now. I'm turning to equations 9.15 and 9.16 in our textbook. The way you define A, again, these things have to be dimensionless, so we're going to start with a factor out here. We're going to have an m omega over 2h bar. That probably looks familiar because our psi, you remember, was defined as square root m omega over h bar. All right, so this is getting us units of inverse length. This is defined as the position operator plus I times the momentum operator divided by m omega. So this is where I'll give you the reminder that in quantum mechanics, this momentum here, instead of being a number, instead of being a thing in an equation, this thing is h bar over I derivative with respect to x, right? And so this thing is an operator. It's not a number. And x similarly is an operator. It just means to multiply by x. So you can kind of get away with thinking of that as a number. If you take the complex conjugate of this thing, A dagger, right? These two, x and p, these are what we call Hermitian operators, meaning they are equal to their own Hermitian conjugate. This is equal to the same thing, but with a minus I in front of here, right? So it ends up equaling the same thing, just with a minus I. So you can kind of think of these as being like different combinations of position and momentum. So this is position plus momentum. This is position minus momentum. And so we just have the over m omega here, so that this ends up having units of length, right? And so the goal is for us to use these ladder operators to kind of replace our position and momentum, because position and momentum are messy operators. I know A and A dagger look like They look messy. Trust me, x and p are even messier. The reason we like these things, the reason these are so important to us, is because of the effect they have on an energy eigenstate. Let me show you what I mean. We call these the raising and lowering operators. Here's why. If you take the lowering operator A and you act on your energy eigenstate phi n, so this thing we've taken the last half an hour to look at, if you take this special combination of position and momentum and use it to act on any of these energy eigenstates, you end up with another energy eigenstate that has been lowered by a level. The only thing you have to do is it costs you a square root of n. So in other words, this is an operator that when you attach it onto this wave function, you get out the next lowest energy eigenstate times the square root of your index from over here. So remember we drew this ladder earlier, right? We drew these energy eigenstates, these energy levels. A is the thing that takes you from one level down to the next. So then you could apply A again and go from this level down to the next. A is the thing that takes you down the ladder. On the other hand, a dagger is a raising operator. If you act on phi n with this, you end up with a different factor out here, n plus 1. I'll show you why that's important in a minute, times phi of n plus 1. So in other words, a dagger is the thing that takes you up an energy level. So if I start here, I go up a level. If I start here, I go up a level. So A is the thing that takes you down the ladder. A dagger is the thing that takes you up the ladder. And that's interesting because think about what happens if n equals 0, right? If I take the lowering operator and act on phi 0, it looks like I'm in a little bit of trouble because it looks like I'm supposed to get a phi negative 1, and none of the Hermite polynomial stuff makes any sense if you put in a negative 1. But this is the thing that saves you, because here you've got square root of 0 times some function that doesn't exist, but it doesn't matter that this function doesn't exist because you're multiplying by 0. So in other words, if you try to go below the lowest level, you get absolutely nowhere. It's really cool. This machinery is really cool the way it's set up. It's also really cool because you can combine these to get something called the number operator. I'm going to show you why it's called the number operator. The way you get the number operator is you take a dagger and A and then act on both of those with phi n, right? So if I take those and I put those onto a phi n, right? So we'll just put a colon there to say we're acting on phi n. Let's take a look what happens to the first one. So I would have a dagger acting on A on phi n. So A on phi n gives me square root of n times phi n minus 1. Right? It lowers the energy eigenstate and gives me the index. Well, this index can come out front, right? This index can come out here because it's just a scalar. Scalars are allowed to migrate across operators without a problem. And so now you have a dagger. Let me get a different color here. Now you have a dagger acting on phi n minus 1. Right? A dagger acting on phi n minus 1. Well, we know what a dagger does, right? A dagger is the raising operator. A dagger is the thing that takes phi n and moves it up. Except now I don't have phi n, I have phi n minus 1. So this is going to get me back a phi n. It costs me multiplying by n plus 1, right? Or square root of n plus 1. Right? So if I've got n minus 1 here, getting plugged into n here, I've got n minus 1 plus 1. I just have square root of n. So I've got root n times root n. Last time I checked, I don't think they've changed this rule, that equals n. So this number operator is really cool because if you take number operator and act on phi n, you just get out the energy level, the energy index n times phi n. It's really cool. It's super amazing. This is one of the coolest results in an intro quantum mechanics class, is how this number operator just gives you back the same wave function times the index n. So that's all I had in my notes to talk about for today. I'd be happy to take any questions, comments, anything that has stood out to you, anything that confuses you, anything you want to go back and look at. I'd be happy to engage folks in conversation over in the chat window. Alyssa tells me this is slightly more confusing than I thought it would be, but that is normal. The good news is, I mean, if you really want to see confusion, read the derivation of this thing. The derivation of the quantum mechanics harmonic oscillator is a thing you read once in your life and you say, okay, I understand that somebody did this and that the math works out. I never want to do this myself. It's that level of thing. The most important thing, though, like I said, is these general properties, that it's got these evenly spaced energy levels. I'll also add just a reminder that I've got a video about the quantum harmonic oscillator and how we can make a simulation out of it. Let me get that link for you to post into the chat. I'm glad my students are learning to expect to be. The thing is, it's okay to be confused by quantum mechanics, right? We're all confused by quantum mechanics. It's the weird part of the universe. Let me get this link for. Here we go. Get shareable link. There we go. We'll say here's a video with a simulation exclamation mark. Then, yeah, so I've posted that video. Then you can be confused by the math and by the animation. One of the other neat things about this, let me just talk into the air for a second here, is you can use these energy eigenstates to form things that are called coherent states. They talk about those in the textbook. I also mentioned those on the pre-recorded video. I had a professor in grad school who absolutely loved coherent states. He wore a t-shirt that said coherent states, good for everything, because they really are good for everything, and you can use them in all sorts of physics applications. You know, if like even in something in like setting up a laser, you can set up a laser to have this kind of coherent state kind of thing. It's all kinds of really neat stuff. Since we got a couple minutes left on the stream, why don't we just take a look at one more item of business. So for class, just for convenience, I've taken the last few assignments and just combined them into a thing called final assignment here. I am trying to err on the side of this thing being straightforward rather than burdensome, because I know folks are scattered about. I know support is difficult to find, and I know I know some of you probably left your textbooks in your dorm room thinking you would be able to get it back. So basically, for the rest of this semester, we're going to be looking at chapters 7, 8, and 9. I've just picked 2 or 3 problems from each of those chapters. These are the ones from chapter 9. They should be pretty straightforward. A couple of them ask you to use the raising and lowering operators. That's just so that you have experience working with those, because that's a thing that grad schools and REUs will ask you to work with. So like, for example, problem 9.2 says, show that the action of a dagger on an eigenstate of H produces an eigenstate with the eigenvalue raised by 1 quantum. Yeah, that's basically the thing that we worked through here. You're basically proving this piece here. Let's see, what else do we have? We got 9.4. My main piece of advice for 9.4 is to use Wolfram Alpha. It'll ask you to do an integral, which is Wolfram Alpha's domain. And then 9.11, it gives you a wave function in, or an initial wave function in Brockett notation. And it basically is asking you to do the same kind of thing you've done before. It says find the normalization constant A, find the time evolved state psi, calculate expectation values. It's the same kind of thing you did back in the infinite square well. You just have different basis now, right? So now instead of using those signs, those nice, neat signs, you're using these phis that are crunched together there. And honestly, if you even wanted to take your to take this code, which already gets out the phis for you, you could in principle use this and carry out the integration. I know half of you already have a code that will integrate the wave functions here, so you could in principle use this piece of machinery to satisfy that problem as well. So we've got a couple more minutes. What I will do is stick around for any other questions to come in through the chat. Otherwise, I want to thank you all for your time. This is definitely a brave new experience for all of us. Would be happy to receive any feedback you've got. Again, I'll have this link's available in the chat notes. It's also saved in our class folder on Google Drive, so you should be able to get it there. But yeah, if you've got any other questions, I'm happy to have a look at those in the chat window. And otherwise, I'll be sending you a link on Friday for us to have some office hours. We can get some face-to-face time over Google Hangouts. I'll be emailing you the link for that on Friday. I'm going to see if I can get that link ahead of time. If I can, I'll go ahead and send it. If not, I'll send it to you because it'll be online anyway. You can look at it in your email. All right. Thank you all for your time. Have a wonderful afternoon.